Hello and welcome to the first video of section 1.8 on continuity. Everything in this video will build upon the intuition for limits that we developed in section 1.5. A common misunderstanding of limits occurs among many calculus students. When they learn about limits, they wrongly believe that the actual value, f of a, influences the existence or value of the limit as x approaches a. It's natural to expect the limit and the actual value to coincide. For most natural phenomena, they are equal. Take for example motion. If you were to look up and notice a large object directly above you that appears to be falling, you would move quickly away from your present location. You naturally expect the object to follow the trajectory it's been on while you've been observing it. We expect continuity. That is, we expect the limit of the object, the motion just before your current observation, to equal the actual value. The dictionary describes continuity as uninterrupted flow, and that is what the mathematical definition guarantees. A function f is continuous at x equals a if the limit as x approaches a equals the actual value f of a. That is, we have an uninterrupted flow. The location of the point at x equals a is the one implied by the trend of the previous points. The limit equals the actual value. An intermediate step towards continuity is one-sided continuity. If the actual value equals the left-hand limit, the function is continuous from the left, and if the actual value equals the right-hand limit, the function is continuous from the right. In this graph, the function is continuous from the right at x equals a, but is not continuous from the right at x equals b. The function is continuous from the left at x equals b, but is not continuous from the left at x equals a. Like with limits, the two-sided concept is supported by the one-sided. A function is continuous at x equals a if and only if it is continuous from both the left and the right. Usually, we are interested in continuity at more than a single point. We say that a function is continuous on an interval if it is continuous for every point in the interval. Visually, a function is continuous on an interval from a to b if the curve is unbroken. That is, if an ant were to crawl along the function, dragging a pen behind itself, it would trace out the entire graph of the function on the interval. For example, take the graph y equals 1 over x. The function is continuous on the open interval negative infinity to 0, and continuous on the open interval 0 to infinity. In other words, y equals 1 over x is continuous on any interval which doesn't contain 0. Continuity is important because it is a prerequisite for doing most of what we want to do in calculus. We cannot do calculus at discontinuities. For instance, where would we put the tangent line at x equals a? At the actual value or at the limit? At x equals b, would we have the tangent line from the left or the tangent line from the right? In section 2.2, we will discuss the concept of differentiability and how continuity is connected to it. A quick warning, sometimes we cannot take a derivative even though the function is continuous. For instance, the function is continuous at a, but the tangent line from the left and the tangent line from the right have different slopes. Therefore, the derivative at x equals a does not exist. If a function is not continuous at a point, then it is called discontinuous. What does it take to be discontinuity? Well, let's start with what it takes to be continuous. From our definition, to be continuous, the limit and the actual value must exist and must be equal. With this in mind, we describe the general types of discontinuities which stem from breaking either 1, 2, or 3. In both graphs, there is a removable discontinuity at x equals a. A removable discontinuity is the case where the limit exists but is unequal to the actual value. This leads to two graphs. One in which the actual value exists but is unequal to the limit, and another in which the actual value does not exist. We use the term removable because we can make it continuous by redefining the value of f at x equals a to equal the limit. The next graph shows a jump discontinuity at x equals a. A jump discontinuity is the case where the one-sided limits both exist but the two-sided limit fails to exist. Notice that the ants can only meet at x equals a if they jump to another level. Our last graph shows an infinite discontinuity. An infinite discontinuity is the case where a one-sided limit is infinite. The type of a discontinuity is not determined by the actual value f of a. It is solely determined by the limit. You've seen the basics, now work towards mastery through practice and study.